Okay, well, it's great to have Qingyuan Jiang speaking today from University of Edinburgh on the derived category of Quot-schemes of locally free quotients.
Okay, thank Aaron for the introduction, and thank you very much for the invitation. And it's a great honor to speak on this derived seminar. So the topic I want to talk about today is on the derived categories of Quot-scheme of local free quotients. But before going into the details, so let me start with the actually two motivating examples. So this example are essentially all due to Olaf, and the setup is as follows. So okay, is that okay? So X to be a quasi-compact, quasi-separated scheme, and that this one to be a Kuzu-regular immersion. So for simplicity, let's assume Z actually is the zero locus of a section of a line bundle, of a vector bundle. So where S is belong to, here it is a vector bundle of a rank, let's say n. Okay, so for this data, there are two very canonical constructions. So one is called blowup. So the blowup, the X, it can be defined as the proj, relative proj of this graded algebra. Okay, and then it has a natural map, a projective map to X. And over Z, the inverse image of Z there will be so-called, this will be a Cartier, effective Cartier divisor called exceptional divisor. Okay, and then here actually there will be, this is a projected bundle here, so it's project bundle. And the other very interesting construction is called, it has certain, I don't think it has some universal accepting name. So whether it's called universal hyperplane section, or it's called Cayley's trick, Cayley's trick. So I first learned this example from Richard Thomas, and he called it Cayley's trick. So and so this construction is as follows. So let me mark the maps here. J. Okay, so because essentially it's something like this. So if we consider G to be the co-kernel of this section map, then the projectivization will be, let's call this HS, will be a divisor of this vector bundle. So the geometry is something like this. This will be pi, this will be Z. And then this, here, this actually, let me call it P, Z. So this is still a projected bundle here. But the interesting thing about this pi will be, then this is generically, so it's generically project bundle, but the rank of this map will jump. And this I is a so-called O11 divisor, but just I is the inclusion of a divisor, of an effective divisor. Divisor of the line bundle OPE1. Okay, and so this, you see these two situations a little bit similar, and actually they can be, this similarity can be expanded using certain using HPD actually, but let's not talk about that today. So there are two very interesting theorems due to Olaf. First is that So for the blow-up situation, the derived category of blow-up will be like one copy of this dx and many copy of dz. So let me starting with 0 n minus 2. So this is actually n minus 1. And that like a relative dual-lighting. So I be a little bit weak here, but this D actually can be taken to be whether perf or dB or dQc, the quasi-coherent cohomology. And there actually a relative dual-lighting sheaf exists, which is nothing but this one. And then this actually gives rise to a self-functor. So relative self-functor. Autoequivalence, and it will kind of give a mutation of the whole thing. So it will assign this perf zk to perf zk plus minus n minus 1. Okay, so this is the first formula for blow up, and second formula is for this Cayley's trick or universal hyperplane. So it looks very similar, but in ways due to this picture. So, let me call this P, J star, P star, dz, and then we have a certain pi star dx, and so the sub-index indicates it is a twist by line bundle, and also in this case a relative self-functor exists. Pi we assigned this dx k to dx k minus n minus 1. So basically this means formula we can mutate here to here. So we have actually a family of semi-Massonite decomposition. Okay, so my claim is that all of this under the condition that X is smooth, and just that in some places I assume it's scattered 0, but in some other places he did not mention that. But my claim is that above holes. So the claim. So holes without any condition, without any further condition, except from the fact that X is quasi-compact, quasi-separate.
Can I ask, what do you mean by relative self-functor?
Oh yeah, I will explain more that later. But essentially, it essentially means that it's so the relative self-functor essentially will mean this category over a base, and then this we will define a home which is for elements for D here, and then the relative self-functor means that something like this is true. AB du will be SB SA. So this kind of derived this DQC valued home has this relation. Okay, we may talk about this more like in the global case. And okay, so and Z is quasi-regular inverse. Okay, so let me explain a little bit why this is true. So the explanation is as follows, and actually goes 2 steps. So first, let's look at the local situation. the local model for blowup is actually very great. So for blowup, the local model looks something like this. So we have 0 inside this a n, and then if we consider blowup of 0 a n, so and this will be let me call it E0 here. This will be I, J, P, I. So the local model for this one actually is can be embedded into so the local model is it can be defined as the 0 locus of xi j minus xj xi for every I smaller than j inside this an times p minus 1, but let's write it as spec z x1 to xn times proj z capital X1 to xn. So this is the local model for this blowup, and learn to prove this decomposition in this local model is actually very simple. So, proving local model. So, and we want the Derived category to have a decomposition of this form. So let me call this just point, and then we want pi star an, and learn the point twist by 1. Wait, do I no, twist, do not twist, and here twist it by -1. Okay, so first for the fully feasible part, it's actually very easy. So it's exactly the same as the absolute case, like in the usual case. So let me omit that part. And for the generation part, so in this very, very nice local situation, so this blow up, so this category, here D, let me take D to be the perf. Then this is generated by O1 up to ON. Wait, let me think. P minus 1. Okay, so but on the other hand, so we have this resolution, so we can resolve this phi 0 phi to be this functor applied to O point will be this two term. And now
how do you know this objects generate O up to O n minus 1?
Oh yeah, because it has this has a affine map to the Pm n minus 1, and the perf of this one will generate the perf of this one, like in the at least in the classical sense, like the right orthogonal is 0, and we know that this one is generated by O to O1 to up to O n minus 1. Okay, and there, so okay, so from this one there, because it's easy to prove generation, because here we have O, and here we have this complex, so we actually got O1, and then next we got O2, and up here O minus 1. Okay, so therefore in this local case, the generation is still very easy to prove. Okay, now let's look at the universal hyperplane, the Cayley's trick. So the local model is a little bit similar to that one, so it's kind of like this. An here, let me call it just H, and this call this P0, j I p pi, but this now is embedded as a O1 into this an times p n minus 1. Okay, so the local model looks something like this. So the local model for this H is the zero locus of x, xn xn of this spec z x1 to xn times pro z x1 to xn. So this is I usually would like to call this O11 divisor, but yeah, it's kind of linear in degree 1 in both of the variables. Okay, so learning this for this situation we want to prove. So we want to prove that let's say proof H is sorry, O point, but let me still hold 1 and learn dx 1 up to dx n minus 1. Okay. That's probably need to another page. Okay, and learn to prove this. Learn the fully fixed one is exactly the same as before. So this is easy. Let me omit this part. For generation, so okay. So for generation, it's a little bit similar as before. So it's O point. Now we have this resolution, but the resolution now looks something like this. So it's a Quadruple resolution in this case. Like I, O, okay. So O1 n I. Wait, I think it's n minus 1. And O1, wait. I feel that. Okay. So it looks like this. So this will be the Kuzu resolution of this image. And now so the generation now is still very simple because in this case H is still generated by O1, this is O(n minus 1). And there, so here we got O1, here we got O(n minus 1). But on the other hand, since we have this formula, so this will implies now this term will contribute O. And now we hit every generator, so therefore this collection is full. This semi-solid decomposition is full. So general whole category. So this expands the local model. So is there any question for local case? Okay. So now next step will be from local to global. Okay.
Sorry, what was X in that semi-orthogonal decomposition? What was X?
X. Oh, sorry. X will be the AN.
Oh, okay.
In this case. Yeah.
Thank you.
X will. Thank you. So the key point to passing from local to global is the following. And so the upshot is zeros key locally. So this both map admits so the situation, so the geometry, let me write it this way. The geometry is a Tor independent exchange of the local model, the universal local situation. So let me write it down a little bit. So, for example, if we in this situation, x, and then if we assume actually locally, then this we only need to assume as long as z is the zero set of functions, zn, and then this set of function will define a map to this an by this f1 to fn, just that's 0. And then this is the below the then the claim is this base change is tau independent.
Sorry, can I make a remark about the presentation? So somehow the screen we see is when you're writing on your own kind of previous writing. You know, like, sorry, do you see the same thing as?
Oh, really?
Yeah.
Oh, no. Okay. Well, what happens? Probably let me pause share and then start share again. Will that work? Is that working now? No. Still on the same page.
So it's the kind of the pre-written thing, and your writing goes over the pre-written thing.
The
really?
Grothendieck theorem you had pre-written is somewhere below.
Oh, really? Oh no, it's oh, this is so strange because okay, so yeah, like on my page it doesn't happen. Probably let me stop sharing and then start sharing again, so to see whether that does it better. Okay, probably let me go. Oh, is that better now? Is that okay now?
Yeah, now the old text is gone and we see the new squares. Yeah, cool.
Okay, great, thank you. Wow, I never saw that happen. Okay, apologize for that. So the claim is this base change is tau independent. And on the other hand, in this situation here, so z, x, hs, p. So it also admits base change from this situation, universal situation, h0, p0, and this is also tau independent.
Sorry, what is the map from X to affine space?
Oh yeah, because I assume it's local, so I assume this z is given by the zeros f1 will be functions on X, and then this f will give the map.
But x and an might have different dimension here.
Oh yeah, yes. But the key here is that the Kuzu condition on this here, on this z into x, already guarantee that this base change is tau independent.
So are you saying that the map is flat or not necessarily?
No, it's not flat.
But who is Tor independent? So you need two morphisms to be Tor independent.
Oh, sorry. Okay. So my claim is that this base change, like the whole diagram is tau independent, means that each square is tau independent. For example, the 0 map to an, z map to x. So for this square is tau independent, but also this square is also tau independent. Okay, is that okay? So I hide the theorem here, so I didn't mention. Okay, then. So probably the dilemma here is that so a tau independent base change of like a blow up of Kuzu regular center commutes with base. Okay. So, okay, how do I formulate it? So let me form it this way. So the blow up of a Kuzu regular center commute with base change. So therefore, the real base change is actually just x mapping to z an, and the z is of course just the pullback of 0. And then this bzx will be the fiber product, the base change of this local blow-up with this divisor, the image of this E0. Oh, so I need to write tau independent here. It's very important. It's tau independent. Otherwise, it's not true. Okay. So therefore, so for this local model. Oh, okay. Therefore, so Zariski design plus tau independent base change there implies that the theorem holds without any condition. Okay, and let me mention here. So this we only use Zariski descent, but we actually know SOD the FPPF descent holds for SOD, and this kind of like a lot of people's work as Elegant and Schindler. So it's for comonoids, and for the FPF, I think Berg. Also, Billmas, Okawa, also Andrew, and so the independent proof the IPF descent. Okay, and okay, so to summarize, so what is common in these two situations is that first they are both, so these two constructions are both Quot-schemes of some sheaf G, which is G has homological dimension equal to 1. I will explain a little bit more what that means. And the second is that we actually to prove that in the local model we have a nice formula for this for this correspondence. So let's assume we insert a correspondence there. It has a nice formula. Oh, some generator here will be a resolution here, like minus n to, and this is kind of the key for us to prove very neatly for the generation part. So for example, this two, this resolution is also equal to resolution in this case, but in general it's not equal to resolution in general. Okay. And also learn the third will be, of course, will be local to global. And this essentially will use Zariski descent plus tau independent base change. Okay, this ends the motivating example. Is there a question? Okay, so if you know that actually this is the plan for this talk. So first I will explain what is Quot-scheme, and then I will explain in the local model what is candidate, what is this lemma for this resolution, and then I will explain the local to global case. And if time allowed, we'll say a little bit about applications and examples. Okay.
Can I ask in the local to global part? So you need the functors, and so you have the functors to prove that they make up similar toggle decomposition. You can do the local case. So
yeah.
if you don't have the functors globally, you cannot glue things together.
Oh yeah, that's kind of the key point. And I think this kind of the good thing about this Quot-scheme construction, because all these functors are naturally correspondence given by Quot-schemes, which are naturally global defined and commutes with base change. So that's kind of the good thing about this Quot-scheme construction. Okay. Okay, thank you. Thank you for the question. And now let's go to the first part, Quot-scheme. So I have written some part before the talk. So if X is a scheme and G is a finite type quasi-coherent sheaf, and learn this definition due to Grothendieck, he first defined it as a functor. So the functor is as follows: for any map, map from T to X, and this functorial point at T will be the set of quotients of this GT. So this GT will just the usual pullback of this G. And this, the key point is this F is local free of rank D. Okay. And learn the Grassmannian's theorem for this is that, so this functor is representable by a projective morphism from this scheme. Let's still call it quad x dg to X, which is finite type projective with a relative ample bundle and together with a universal quotient. Okay, and also, and the second has a lot of nice properties, but the nicest property which relative to our talk here is that the formation of this Quot-scheme commutes with base change. Which means that for any base change G, learn this quot x prime d G prime, if this G prime is the pullback G star x, learn it is nothing but the quot x d G times x prime x. Okay, and the example, one example is when d equal to 1, this is the class of projectivization. So this quot x d equal to 1 G is the projectivization, which is defined as the proj of the symmetric algebra of this G. And the other example is if we let G to be locally free. So let me write it. It's locally free. So learn this quot is nothing but our usual familiar Grassmannian bundle of the due. Okay, so this is kind of the Grothendieck type of notation. So basically up to a due to our usual notation. So this is the usual Grassmannian bundle. Okay, and the remark here is that from this, because it's commutes with space change, so every fiber of this Quot-scheme is, so if we have a K, a map from spec K is a field, and mapping to this close point X, and with corresponding to, this will be X, field attention, kappa X to K, and then this is nothing but the fiber of X, I need to write G, fiber of G at X times K. So this is here is a vector space. So this is a vector space. So therefore, all fibers of this Quot-scheme are just Grassmannians of vector spaces. So it's so all the fibers are Grassmannians. Okay, and so this actually has a very close relationship with degeneration loci. Let me just mention that. So there's a way to define degeneration loci for this setup. So if X is scheme, and the G will be a finite type quasi-coherent sheaf, and learn that there's something called fitting ideal, which is defined, as the so if G locally admits a presentation, so this is rank n, this is rank m, F doesn't have, okay, let's assume it's rank m, then will be the ideal Okay, the ideal of n minus j of this map sigma, which is generated by n minus j plus 1 n minus times n minus j plus 1 minus of this map. So the key point here is that fitting the theorem due to fitting is that this formulation does not depend on the presentation. So basically it's a well-defined ideal just for the sheaf. And then, so if we define this x greater or equal than j, g to be the zero scheme of this fitting ideal of we have, I think I need to write j minus 1 here. So then the close point of this actually will corresponding to rank of gx greater or equal than j. So that's why I write this notation. And then so the fitting theorem is that this degenerate loci, so degenerate loci commutes with this change. So it means that if we pull back something, then this degenerate loci is a favorable. So it fits very well together with this Quot-scheme construct. Okay, I think I need to speed up a little bit. But a very interesting special case will be if G has finite homological dimension. So let me assume that G has let's assume x is nothing. In this case, the homological dimension of G is just defined to be the supreme this projective dimension of Gx over all points. And so if this is finite, the good thing about this is the rank G is a well-defined function. It's a well-defined function. And is always non-negative. Okay, and so let's focus on the case which homological dimension G is equal to 1. Means that Zariski locally we have a resolution of two terms. So they has rank n, this is rank m. They are both locally free. Okay, and in this case, the good thing about this is we can consider this due the extension group of O together with OX. So this is a sheaf which essentially encodes the derived due information. Okay, so therefore in this case we can consider Quot-scheme of, for example, D plus G and Quot-scheme of this D minus K, with D plus D minus as just two integers. It will be most interesting if we satisfy this condition. So D plus minus delta, where delta will be the rank. Okay, and the previous formula actually fits into this kind of picture. Okay, so let me mention a little bit more examples of this situation. Okay, examples. So one example would be if X is Picard group Picard D of C, line bound of degree D on a smooth projective curve C, then we can define this to be the sheafification of this space, and then this is still is essentially just sheafification of H1 of L. And let's assume that if T is greater than G minus 1, so D equals to G minus 1 plus delta, delta is greater or equal than 0, then so this G will has homological dimension 1, and K will be supported over the so-called Brill Noether locus. And then the Quot-scheme will corresponding to the like symmetric power of curves, and also their generalization, like the moduli of linear series.
And I mean, in that case, are the fitting ideals, are they somehow scheme theoretic definitions of Brill Noether loci? Or?
Yeah, exactly. Yeah, yes, yeah. And actually, the interesting part of this is like when I read the books on algebraic curves, and then I realized that they spend a lot of time, but they really wanted to define it as the zero scheme of fitting ideals, and they really want to define this this modular space to be the Quot-scheme. And the second example will be given by, for example, if we consider sigma will be the big condition on a K3 category, and then this AV will be two numerical class of this D, and let's assume they satisfy the following condition, that the Mukai pairing is greater or equal than 0, and then also just that the image. So this is actually a little bit stronger than we need, but let's assume this. So learn this. They form a fundamental parabola in this inside the central charge form of fundamental parabola. Okay, so in this situation, then we can consider two interesting sheaf. One is the relative extension sheaf. They are both relative extension sheaves. And then the homological under our condition a comma v is greater or equal than 0. Then this one will have homological dimension 1 and the rank av. And then this homological dimension ka will be a v plus 1 and rank will be 0. Okay. And in this case, then Brill Noether loci will just be the one defined by fitting ideals.
So you write x1 of VA, so V and A are vector, like elements in like what does it mean, x1 VA?
Yeah. Actually, there consider so the part will be mapped from this universal space x times so if D lies inside dy, then this would be y times m sigma a times m sigma v mapping to x. And then here we have this quasi-universal sheaves and their extension sheaf, the performer of the extension sheaf on this universal bundle. So, but basically, it's like over every fiber is just parameterized. Essentially, this roughly, essentially parameterize this extension group. Kind of a sheafification of the extension group of every point, the extension group of these two objects. Is that okay? Okay. So also there will be example of like Donaldson-Thomas type of moduli. There's only speculation. I checked some examples. They satisfy this homological dimension 1 condition, but I didn't check in general. So I suspect I think there will be more example in Donaldson-Thomas theory moduli. Okay, so this end up the this second part. Now, okay, so now let's say about what is the relation between this these two type of Quot-scheme, like Quot-G and the Quot-K. So a very easy computation on K0. So in the Grassmannian group of varieties over K shows that the following holds. Okay, let me expand a little bit. What does this formula mean? This actually is a motivic version. We can view it as a motivic version of this combinatorial formula. But which essentially, if we write it in a graph, then it's very easy to remember and very intuitive. So if we somehow imagine this big box, dl, this L actually I defined n minus d. We imagine this large box to be the kind of generator for this whole space, Quot dg. and then we cut it into this line. So we can cut it into two halves, and over each point of the line we have two boxes. And then the claim on this level is this: the big box BLD will be the union of this all these small box BL minus J, something like that. All these small boxes, B1, B2. But for this, I mean this like they kind of made up this. This will be the box which kind of joined together by B1 and B2. So essentially the formula here is just shows that this big box will be the union of all these small box. This left-hand side corner, left corner will be this generator for this quot of K. And on the right-hand side, it will be the parameter space for this quot of K. So in a way, it's a kind of a size of Grassmannian. Okay, so this how to understand this. So let me quickly give you a few examples, like why all the known formulas somehow fit into this formula is as follows. So okay, the conjecture is that there is a Dirac category version for this K0 computation, and the result so far is for Cho group. I can show that. So there's Cho version for that, and for Dirac category so far I can partially show that. So there's only partial result so far for that. Okay. So let me quickly show a lot of examples. So for example, the projectivization case, we can understand using this very simple formula, like a Young diagram of length 1 and height n minus 1 actually. Then this diagonal here will be just this line will cut off at 2 points. And the parameter space for x will be like delta copies. So this will be delta copies. And the parameter space for pk is empty, so it's only 1. Therefore, this projectivization formula can be interpreted this way, and the Cho group can be interpreted this way. And for example, for standard flips, so it's corresponding to L, and D is arbitrary, so D there is -1. And then this cutoff line goes like this. And still, we only cut out 2 integral points. And one point will be the flip point, and one point will be this base scheme, this scheme of the projective bundle S. And
sorry, maybe I missed you, but can you please repeat, when you make this rectangle and you cut it, it's a rectangle of what? Are there some kind of weights, or what is like rectangle means what?
The rectangle will be in the local situation will be the generator for this Dirac category of the large space. It will be the category of this left hand side. This will be the one for this quot G, where G has rank, positive rank. So it has concrete meaning like both in Cho group situation and in Dirac category situation, but essentially like in local situation will be the generator, the parameter space for the generator for this Dirac category. So yeah, so thank you for the question. So therefore, the standard flip can be understood this way. And m equal to 1, there's a formula by Piroskov, which can be understood in this way. There will be like d plus l minus 1 copies of dx, and d plus l minus 1 choose d minus 1 copies of z. And for delta equal to 1, there it can be understood this way. So they're kind of a little bit symmetry between all these examples, but let me not talk too much about that. And also, in this case, you see that this case will be only like one of the parameters is always 1, so therefore only essentially two type of loci contributes to the formula. But as long as one of the parameter goes to 2, then there will be 3 or more like space contributes to the formula. One example would be d equal to 2. There, okay, the formula is a little bit messy, so let's just look at here. So there, this rectangle will be the large space, and so when we cut it, it has 3 integral points, which is corresponding to the x, and then one of these will be the projectivization. The other will be a new contribution. I call it a virtual flip. So then the formula looks something like this. But in this situation, so the semi-orthogonal decomposition, the semi-orthogonal relation between these components are already kind of a little bit complicated. It's kind of nice because they respect their parameters, but on the other hand, they like intertwine with each other. So it's not like we can mutate it to like 3 semi-orthogonal parts, but that will not be natural. The natural way somehow they will intertwine with each other. So this somehow is the how their how the decomposition looks like. So this triangle will be parameter space for this rank G choose 2 copies of the X, and this phi 0 up to phi 4 will be this contribution of this projectivization, and then this 1 copy is given by this virtual flip. Okay. So now let me talk a little bit about the local model. So in the total space of home space of 2-vector space, and then we fix 2 integer d plus and d minus, and then this g plus g minus will be the Quot-scheme of the co-kernel of this tautological map. But actually in this case it has a very concrete description, so let me write it down. So this space X will be the home, all the morphism from W to V, and then we can consider Grassmannian of like V du and Grassmannian of D of W. Then here is that all the maps factor through this Q du inside V, and this will be the moduli of all the maps which first factor through this tautological quotient and learn a map to V. And this space will be just all the maps factor through these 2 universal bundles. Okay, so there this will be the local model for this Quot-scheme situation. So d plus d minus just 2 integers, and V and W just 2-vector space of rank M and rank N. In this situation, so then this R plus R minus, this 2 morphism from the fiber product, they are just all perfect proper morphisms with invertible like dual relationships and dual relation complex. And so kind of in this local model we can make the previous Young diagram precise. Then this perf Z plus will generate by this large box. So they can generate by the pullback of this Schur functor applied to this Q plus or Q plus du. They kind of dual version to each other, so they both works. And then this perf Z minus. So our condition here, so D minus D plus and greater than D plus minus delta is this delta has the difference here. It guarantees that this perf Z is strictly contained in this perf X in this way. So this small box will be the generators for parameter of generator for this perf Z minus. Okay. And now the situation now is so if we consider this correspondence, learn how does this correspondence intertwine with these generators, how they send one generator to the other. And this is kind of the key lemma for our computation. The key lemma here is that the map from the larger one to the smaller one is easier. So basically, whether it's sent to a simple vector bundle or it's sent to 0. So the map from this larger space to the smaller space will essentially have this property. And the interesting part is that the analog of the exact sequence we had before is this one. So this EN type of the map sending the smaller generator, the generator of small space to the large space. And the claim is that we have a type of EN type of complex of this form. Here, all FIs are vector bundles. And they have a very explicit, but also they are copies of generators. And they have this very explicit formula. So let me give you an example of how to understand this formula. So the explanation is that this will be the local correspondence here. And if we take the generator, the small generator, to be the structure sheaf, then what the formula gives is a resolution of the image of the structure sheaf. But the pullback of structure sheaf is the fiber product. So it's essentially just the pull forward of this fiber product, which we actually know is supported on the degeneration loci. So this okay, so and there in this formula, each vector bundle is a direct sum of this form, but actually there is a very nice control of what vector bundle will appear in this resolution. So this is the concrete formula, but in picture it's very easy. So all the vector bundles appear in the formula is corresponding to a Young diagram of this form. So if you have a Young diagram of this size L plus minus L minus and D minus. So essentially we see that this will be the large space and this will small space, and this somehow is the different space here. So this is the size of the different space, and then for every Young diagram here, the one survives is somehow we add this box here and to this component X, and then we keep it as it is here. So this type of graph is exactly all the vector bundles appear in this formula. So it has the size exactly the size of this Young diagram. And for example, so a very special case will be if D minus equal to 1, then this gives exactly the so-called EN complex. Okay. Oh no. Yeah. I think I go much slower than I expected. Can I use 5 more minutes to say about this proof? Okay, sorry. Pause for this. So let me mention how to prove this. So first, so the Kampf's proof of this EN complex, the Egan-Northcott complex. So suppose we have a map between vector bundles VW and W, we do and W do. Then Kampf's proof of how to of EN complex is then we have this projectivization, which is a regular section of a vector bundle. Then we have a Kuzu resolution of this inclusion, and then we can push forward. We can tensor in with OS, and then push forward the whole thing to the X. Okay, and then because in this situation the spectral sequence looks something like this. So essentially we have degree on m-1 and the degree on 0, and then this will be the kinetic morphism. So therefore on the infinite page we will have actual complex of all the surviving terms, all the non-zero terms. So, and this is exactly the Egan complex, the Egan-North complex. So in our situation, it's a little bit similar, but it's kind of, in a way, it's this example a little bit too special in the sense that only 2 degrees contributes, but in general, you cannot expect something like that. And also is that the reason here is kind of a chain is because we are playing with Pn, and the Bequia order for Pn is very simple, just a chain. But in general, you should expect something like a much complicated type of complex. Something. The Bequia order is much more complicated. So it will be a partial order, not a total order. So therefore, the trick for the general situation is that we can to use this special sequence would be too complicated, and but actually we can use a trick essentially due to use post-Nikel system. So okay, let me just say this one. A post-Nikel system is a kind of the good thing about that is survives under exact functors, and then this therefore the first we can, for example, even in this situation, this has a attached post-Nikel system, and then we can put forward this whole system will be a post-Nikel system on X, and so this will be first step, and second step will be because each element is tilting, then we can actually find a genuine complex for the convolution. And then it's just to compute the convolution reduced to a combinatorial problem, which actually has a very nice pattern. So it's essentially like we only show that all the terms shows in that formula look something like this. So this kind of ends up the proof for the local formula. Okay. And a direct consequence for this will be that we will have like all the manifold theories of embeddings from dz minus to dz plus in above situation. It's very easy from this lemma. Also, like we have a simple proof of generation in every special case. Okay, so okay, let me not mention this example, but basically in every example there will be an induction pattern which we can use this very explicit resolution to show the generation. Okay, so this ends up the local situation, and the to local to global, there I just promise that there's a theory which works very well for time-independent exchange inside this generality. Okay, so this is all I talk about today.
Okay, great. Thank you.
Sorry.
Any more questions?
So can I ask something? So these boxes that you're making, so it's a bit like this windows, right? Do you know this window? I guess there are even people in the audience who do this windows. So like waits for a group action, and then is it the same kind of story?
I think a little bit different because here like it's just exactly the Yang diagram. I suspect it should have relationship with the windows, but I think in Windows you have a I think it's slightly different from this parameter. But
you don't have a group acting. Well, these are not VGIT or something.
Yeah. For example, if D plus equal to D minus, then there's a VGIT. But or L plus equal to L minus. But in general, because I have thought about that because it's kind of will be nice if I can use that technique. But the little bit problem will be it will be many space involved rather than just 2 space like in the intermediate one. So for that one, actually, I'm not 100% sure how to use VGIT. But I suspect, I think there will be connection between VGIT with this approach.
Okay. Okay, other questions?
Can I ask another question? So if in this local to global, can it help to deal with K equivalence implies D equivalence? Can one, is it like one of the big questions in this field? Can one somehow apply it to that question? I don't.
Oh yeah, actually, I think sorry, I forgot to mention is that the reason why I made the conjecture is inspired by this relation, like your paper with Sasha, that this relation between L equivalence and D equivalence. So that's kind of the reason I made this conjecture, that because computation, I suspect there should be something like with this philosophy. Yeah, and I think the local to global is a kind of just a very general. I think it's kind of a very general thing that it's just as long as, because we know kind of descent theory holds for the local, and also like kind of the direct category behave very well under tau independent base change. So essentially, that's reduce this as long as the construction is kind of natural, like it's naturally global. Then essentially it will reduce everything to the local situation. Okay.
Any other questions? Ed, yeah.
Sorry, can I just ask you to recap something, because I lost the thread. What? So you have this you say, so if you have a sheaf of projective dimension 1.
Yes.
Then you have so that's G, and then you have K, and then you have this conjecture, which was there a second ago, which was the derived categories of the Quot-schemes of G and K are related in this SOD.
Yes.
Right, and then right, exactly, this conjecture. But later on, there seem to be two integers, D plus and D minus.
Oh yeah, sorry. So this D plus will be fixed for this D, and D minus will be this like varies from all the D minus J. Oh,
I see. So you were proving that the Quot-scheme of K for D minus embeds into the Quot-scheme of
G. Yes. And
I see.
Yeah, and then this kind of this EN type resolution shows that how they kind of intertwine each other inside this space.
I see. So what cases of this conjecture, of the full conjecture, are proved?
Oh, okay. So yeah, it's a little bit embarrassing to say that. So a lot of special cases. So partially, like I can show all the embeddings from DZ minus to DZ plus. But on the other hand, so for the full conjecture, I can show, for example, D equal to 2, a small equivalent 2, L small equivalent 2, delta small equivalent 3, and things like that. So a lot of special cases.
What are L and delta?
Sorry, delta will be the difference between these two. The difference between this, the rank of this tree.
Oh, I see.
Okay, and D will be this D. L actually will be the L here. So basically, if the parameter is small equivalent 2, or in certain cases small equivalent 3, I can show it's the full decomposition. Yeah. The problem is when equal to 2 is already like 3 strata involved, and they kind of intertwine with each other. And for it's kind of embarrassing in the sense that usually I should expect that after computing so many special cases, the general pattern should show up. But in this case, it's up to the special case I computed so far, the general pattern still did not show up. Or probably already showed up, I didn't realize. But yeah, so this is still kind of a partial result in this sense.
I don't know. My experience with Grassmannians is you assume once you've done it for G2n, you can do it for all Grassmannians, and it's just not true. Grassmannians just...
Yeah.
Okay. Thank you.
Thank you.
Okay, if there are no more questions, then we can all hop over to Gather Town.